Hi everybody, this is Dr. Niger, the Chem calculation screencast. This screencast is going to look at the four phases of an acid-base titration where you're titrating a weak acid or base with a strong acid or base. If you are interested in the four phases and the calculations for a strong acid, strong base, or strong base, strong acid titration, please go look at that separate screencast. Okay, now when we do this, we're going to see the same general phases as with a strong acid, strong base titration. All right, but pH calculations are going to be more complicated because the conjugate of a weak acid or weak base will influence pH. All right, so you'll see the phases are going to be the same, but the calculations are going to be a little bit more complicated. We really have to pay attention to what's present in solution after the neutralization reaction has occurred. So that's where your ice charts are going to be really, really helpful. All right, so let's talk about these four phases. All right, so as before, let's say that for this example, what is my problem? It's a weak acid with a strong base. Let's say a weak base with a strong acid. Okay, so initially, no strong acid added. All right, so that's going to be our first phase. All right, so pH will depend on the concentration of our weak base and its Kb value. All right, we'll do the dissociation of that weak base. Using its Kb, we can calculate the percentage or the concentration of hydroxide present, and then from there, the pOH and pH. All right, so I would expect to see a high-ish pH. I say ish there because if it were a strong base, I would expect to see it up near 14. But because it's a weak base, it's gonna, I don't know, 9 to 12 range-ish. All right. So B, this is before the equivalence point. All right. So at this point, the moles of base will be greater than the moles of acid. We'll have added in some strong acid to neutralize some of that weak base. All right, but we're still going to have excess weak base at the end. All right, the difference here is at the end, both the weak base and its conjugate acid will be present. All right, and that is also known as a buffer. All right, so we'll need to use the Henderson-Hasselbalch equation to determine what the pH is going to be of this solution. All right, C, we're going to be at that equivalence point. All right, so that means the moles of the base will be equal to the moles of the acid. All right, and at this point, only the conjugate acid remains. All right, so we'll need to use the concentration of that conjugate acid and its Ka to determine that pH. All right, again, we'll write a dissociation or an ionization because it's a conjugate acid. All right, and we'll use that to determine the concentration of H plus present, and then we can calculate pH from there. All right, and then finally, D, all right, this is after the EQ point. All right, so in this case, the moles of base is less than the moles of acid. All right, so the concentration of strong acid in excess will determine our pH. All right, and we'll use its ionization to determine the amount of H plus present, and then that will be used to calculate that pH value. All right, so those are our four phases. All right, what does the titration curve look like in this case? All right, so again, we're going to have pH on our y-axis. I'm doing an example, so we'll do acid added on that x-axis. That should be in milliliters. All right, 1, 2, 4, 5, 8, 10, 12, 14. All right. I'm not going to put any numbers on that x-axis because it depends on the concentration of things, how much I have to add. So we're just going to do a general shape. All right, so this time, because I have a weak base initially, I'm going to assume the pH, let's just put it right about here. All right, it's not going to be up there near 14 like I would expect for a strong base. It's going to be a little lower. All right, but similar, I'm going to see a decrease in that pH value as I use some of it up. All right, then I'll see a sharp drop when I get equal amounts of moles. Oops, I'm a little low there. Let me fix that. And then it's going to level off again. All right, now the equivalence point, I didn't do a very good job here. Hold on. I want to make sure this is very clear. All right, so let's, maybe not so much. All right, the equivalence point this time will not equal 7. All right, it should be less than 7. All right, the reason for that is that at the equivalence point, what remains in solution is a conjugate acid, right? And if it's an acid, we should have a pH value less than 7. All right, so your equivalence point when you do a weak base with a strong acid should always be less than 7. All right, and then as we move through the final two phases, we'll see a decrease into these lower pH values, but I've probably drawn it a little low. I don't think it's going to get all the way down to 2 because remember, oh, well, no, it's a strong acid. Yeah, well, that's fine. All right, so we're going to have part A at the beginning, all right, and then this pH will be basic, but not too high. All right, then we're going to have this piece, B, all right, we're going to have acid reacting with weak base, and we'll have a buffer forms. All right, and then we see that equilibrium point, and then down below, I should see here, this is going to be our excess strong acid. Okay, so those are the 4 phases. That's what it should look like in general. You see that the general shape is the same as a strong with a strong. It's just the starting point and the equilibrium point, or the equivalence point, are going to be in different spots. All right, so let's try these 4 phases. All right, calculate the pH of a 25 milliliter, 0.1 molar acetic acid sample after. So we're going to be starting here with a weak acid, and we're going to add in a strong base. All right, so this is going to be weak acid plus strong base. All right, so our phases are going to be the same, but we're going to have different components present. All right, so the only thing present is acetic acid. All right, so I'm going to show the ionization of acetic acid. Put that in the presence of water. Double-headed arrow because it's an equilibrium. And we're going to form hydronium and the conjugate base, acetate, H3O2 minus. Okay, so we set up our ice chart. All right, our initial amount of acetic acid, we have a concentration of 0.10 molar. All right, water is going to be in excess. All right, we won't have any hydronium or acetate. All right, the change is going to be X, so minus X plus X plus X. So we'll have 0.10 minus X, X, and X at equilibrium. All right. Whoop. Oh, it's disappeared again. Hold on. Go back. Let's see if it came back. Yes, it came back. Okay. All right, so this is a acid, so Ka, that's going to be equal to the concentration of hydronium times concentration of acetate over the concentration of acetic acid. All right, so I know the Ka value here because I went and looked it up. All right, if you don't know it or it's not given in the problem, all right, just make sure you go use Google or your textbook and you can find it. But for acetic acid, it's 1.8 times 10 to the negative fifth for my Ka value. All right, so I'm going to end up with x times x divided by 0.1 minus x. All right, now, if I look at that Ka value, it's very small. All right, so don't expect a lot of my acetic acid to ionize. So this x that I'm subtracting out of 0.1 is probably also very small, probably less than 5%. So I'm going to ignore that negative x and just have 0.1 there. All right, so I multiply both sides by 0.1, and then I'm going to need to take the square root. And I find that x is going to be equal to 1.34 times 10 to the negative third molar. All right, and in fact, that is less than 5% of 0.1, so I'm all set. All right, so that means at equilibrium, I have 1.34 times 10 to the negative third H3O plus present. All right, so that is going to determine my pH value. So pH is the negative log of that hydronium concentration. Excuse me. So the pH will be the negative log of 1.34 times 10 to the negative third. So our pH initially is 2.87. All right, now that's low, but it's not super low. All right, so that's reasonable for a weak acid in solution. All right, now I'm going to start to add some of my strong base. I'm going to add 10 milliliters of 0.1 molar NaOH. All right, now I like to work in the mole once I start adding stuff in. You can do your dilution calculations and have molarity, but for me, it's a little bit extra work, and visually, it's easier to compare moles to moles. All right, so that's how I like to do it. So the first thing I need to know, well, then, is how much acid do I have present? So the moles of acid. So if I go back up to the top, all right, moles of acid are going to be equal to the molarity of its acid times that volume. All right, so in this case, 0.1 molar times 0.025 liters. All right, if I multiply that out, I have 0.0025 moles of acid. All right, so 0.0025 moles of that acetic acid. All right, now for the moles of the base, all right, I have moles of base. It's going to be equal to the molarity of the base times the volume of the base. So that's going to be equal to 0.1 molar times 10 milliliters, 0.01 liters. All right, so that means initially I have 0.001 moles of base. All right, so as you can see, the moles of the acid are greater than the moles of the base. So we're not at the equivalence point, we are before it. All right, so that would lead me to assume that my pH value should still be somewhat acidic because I haven't used up all of the acid that's present. All right, but we got to run the reaction to make sure. So we've got acetic acid, HC2H3O2, aqueous, plus NaOH, aqueous. This is going to be an equilibrium. Oh no, not this one, sorry. This is going to go fully because I'm going to use up all that acid. All right, and I'm going to form H3O plus. Oh no, what am I doing? It's a neutralization reaction. H2O, liquid, plus NaC2H3O2, so sodium acetate. All right, now I could again write the net ionic here. All right, but for me, I'm just going to leave it as is. ICE. All right, so initially in terms of moles, I have 0.0025 moles of my acid, and I have 0.001 moles of my base. No water, no sodium acetate. All right, so I'm going to use up all of that acid, which means I'm going to need to react that same amount. I'm going to use up all of that strong base, which means I need to react that same amount of my acid. And I'm going to form that amount of water and that amount of sodium acetate. All right, so that means once that reaction's happened, I'm have 0.0015 moles of that acetic acid, no strong base. 0.001 moles of water is formed, and 0.001 moles of sodium acetate. All right, now I have to ask myself, what is present in solution? All right, so I have a weak acid right here, but over here, this acetate piece, all right, that is my conjugate base of that weak acid. So I have some weak acid and some of its conjugate present. And when that happens, you have formed a buffer. All right, so that means to calculate the pH, I need to use the Henderson-Hasselbalch equation. All right, so remember the Henderson-Hasselbalch equation tells us the pH of a solution is equal to its pKa plus the log of the concentration of the base divided by the concentration of the acid. All right, well, I can determine the concentration of the acid in the base. I need to take my moles and divide it by my total volume. I'll do that in a second. All right, I also need the pKa. All right, so remember, just like pH, pKa is the negative log, but of the Ka value. All right, so in this case, negative log of 1.8 times 10 to the negative fifth. All right, so that pKa is going to be equal to 4.74. So I'm going to need that value. All right, now the molarity of my weak acid is going to be equal to the moles divided by the volume. All right, I had 25 milliliters, and I added 10. All right, so 0.00150 divided by a total of 0.035 liters. All right, so that means my concentration of acetic acid that remains is 0.043 molar. All right, I'm going to do the same thing for my base, the moles of my conjugate base divided by the volume, so 0.001 divided by the same volume, 35 or 0.035 liters. All right, so I'm going to have a concentration of 0.029 molar of that conjugate base. All right, so now I can go back up into my Henderson-Hasselbalch equation. So 4.74 for that pKa plus the log of 0.029 molar divided by 0.043 molar. All right, plug that into my calculator. I'm going to get negative 0.17 if I take the log of that division, and then plus the 4.74, I get 4.57 for my pH. All right, so the pH has increased because I used some of my weak acid and formed some of the conjugate base. So it's reasonable that it has gone up. All right, and it went up a decent amount. It went from almost 3 to almost 5, so almost 2 pH values. All right, so again, buffer. So you got to remember the Henderson-Hasselbalch equation. You got to know how to calculate pKa's. Okay. All right. Next. Now we're going to add 25 milliliters total of 0.1 molar NaOH. All right. So again, the moles of acid are the same, 0.0025 moles. All right, because that's what I had to start with. Now my moles of base are going to be equal to the molarity of the base times the volume of base added. So that's going to be 0.1 molar times 0.025 liters. All right, so the moles of base that are now present are 0.0025 moles. All right, so hopefully you look at this and you say, oh, the moles of the acid equal the moles of the base. Therefore, I must be at the equivalence point. All right. So I'm going to use again my reaction. So I have HC2H3O2. I'm going to react that with my strong base, NaOH. And we're going to form water and NaC2H3O2. All right. Set up the ice chart. Initial amount of acetic acid, 0.0025 moles. initial amount of base, 0.0025 moles, no water, no sodium acetate. All right, now this time it's the same. So we're going to change the whole thing, minus 0.0025. So we're going to use up all the acid, we're going to use up all the base. All right, on this side, we are going to have water form, 0.0025 moles of it, and we're going to form the same amount of sodium acetate. All right, so at equilibrium, we'll have added some water molecules, and we have added some sodium ions and acetate ions. All right, now, if the sodium acetate wasn't there, I would say the pH is 7. All right, but in this case, if I look at that salt, now the sodium ion is the conjugate acid or the ion that forms because of the dissolution of NaOH. So it's not going to affect pH. It's not going to start picking up NaOH groups, and it's just not going to do that. But that acetate, that is the conjugate base of a weak acid. All right, so this value, this is moles of acetate. And that will influence the pH. All right, so what I need to do with that value is I got to figure out how much dissociates or how much ionizes back into the acid form. All right, so let's start by doing the concentration. All right, so that's going to be moles divided by volume. All right, our total volume at this point is 50 milliliters. All right, so we'll take our 0.0025 moles and divide that by 0.050 liters. All right, so we have a molarity here of 0.05. Yep. All right, so now what I need to do is think about the the ionization, of this weak base. So I start with C2H3O2 minus, that's your acetate. In the presence of water, is going to accept a hydrogen ion, forming acetic acid, and leave behind a hydroxide from that water. All right, so we set up a new ice chart. All right, the initial amount of acetate, 0.050 molar, that water will be in excess. All right, we won't have any of the acetic acid or hydroxide present. All right, now we're going to change a certain amount of it depending on the Kb value for this base, and we're going to form a certain amount of our two products. All right, so we're going to 0.05 minus X plus X and plus X. All right, so we need Kb, right? This is a base, so we're going to need to know what the Kb value is of this base. All right, I'm going to give myself a little bit of room here. Now remember, Kw is equal to Ka times Kb, which means Kb is equal to Kw divided by Ka. All right, and Kw is 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, because that is our Ka for acetic acid. All right, so our Kb value here is going to be 5.6 times 10 to the negative 10th. All right, the Kb expression is going to be equal to the concentration of hydroxide, concentration of acetic acid, all over the concentration of acetate. All right, now, as you can see, that Kb value is very small, which means the amount that is changing here is going to be very small. So that minus X can go away. It's going to be less than 5%. All right, so we have 5.6 times 10 to the negative 10th will be equal to X times X divided by 0.05 minus X, but we're going to take out that minus X. So multiply both sides by 0.05, then we take the square root, and we find that X is going to be equal to 5.3 times 10 to the negative 6th molar. All right, this is the concentration of OH minus. All right, that is a strong base that is present in solution. That is going to dictate our pH. So we'll calculate pOH using the negative log of that value. I'm running out of room, so I'm going to shorten things. All right, so our pOH is 5.28, and the pH is 14 minus the POH, so that's going to be equal to 8.72. All right, so we ask ourselves, is 8.72 a reasonable answer when I have a weak base present in solution at the end of this titration step? And I should say yes, it is greater than 7, but it's not way up there where I would expect to see a strong base. So 8.72 is a reasonable answer. All right, now, as you can tell, this is a serious calculation. All right, this is the hardest step in a titration of a weak with a strong. All right, so make sure that you understand what we were doing here. You do the neutralization reaction first, determine how much of that conjugate is present after the acid and base have neutralized. Then you take that conjugate, ionize it or dissociate it, depending on whether it's an acid or a base, and use its Ka or Kb value to determine how much hydroxide or hydronium is present. And then you may calculate pH. All right, last step, addition of 35 milliliters total of that strong base. All right, so amount of base is the molarity of the base times the volume of the base. All right, so this time we have 0.1 molar and 0.035 liters, so 0.0035 moles. All right, so moles of acid are still 0.0025, and now moles of base are 0.0035. All right, so hopefully we recognize that the moles of acid are now less than moles of base. All right, so we passed the equivalence point, and now we're going to have excess strong base in solution when we're finished with the titration step, which tells me my pH value in the end should be very high. All right, but we got to prove it. So HC2H3O2, so there's our acetic acid, plus our sodium hydroxide. We're going to neutralize to form water and our sodium acetate. All right, we set up our ice chart. Initial amount of acetic acid, 0.0025 moles. Initial amount of sodium hydroxide, 0.0035 moles. No water, no sodium acetate. All right, the change this time is going to be the acetic acid. We're going to use up all of it. It gets neutralized. 0.0025 gets lost. All right, we're going to use that same molar amount of our base, and then we're going to form those amounts of the water and the sodium acetate. All right, so I won't have any of my weak acid left. I'll have 0.0010 moles of strong base left, and I'm going to form 0.0025 moles of water molecules and 0.0025 moles of sodium acetate. All right, so it's going to be tempting to look back at that sodium acetate again, because you're like, okay, I have more of that than I have of the hydroxide. But the reality is the hydroxide is so much stronger than that acetate anion that the acetate, it's not gonna matter. All right. So when it comes to determination of pH, I need to focus on this hydroxide amount that's present. All right. So the molarity is going to be equal to moles divided by liters. All right. So I'm going to have 0.001 moles. And my total volume now is 25 plus 35. So that's going to be 60. Whoops. I need that in liters. All right. So the molarity of the NaOH that remains afterwards is going to be equal to 0.017 molar. All right. And because that base dissociates fully, that is also equal to the concentration of hydroxide ions that are present. All right. So I can use that to calculate POH using the negative log of the 0.017. And I'm going to get a POH value of 1.77. All right, so pH is going to be equal to 14 minus that POH value. All right, so I'm going to get an answer here of 12.23. All right, so I asked myself, is that reasonable? I have a lot of strong base left. I should have a pH value that's pretty high. And 12.23 is much higher than the 8.72 that I saw with my acetate from the third step. All right, so this is a very reasonable answer. Okay, so now we're going to sketch the titration curve for this experiment. I'm also going to include I want to make sure I include the equivalence point too. All right, so let's draw our axes first. Oh, that's a little quicker. That's better. All right, pH is going to go on the y-axis. This is base added, which will go on our x-axis in milliliters. All right. All right, so 2, 4, 6, 8, 10, 12, 14. All right, we ended up around 40, so 10, 20, 30, 40, 50. Oops, I almost skipped 30. 30, 40, 50. All right. All right, so A, no base added, weak acid. All right, so we saw that when we had only weak acid present, our pH value was low, but not super low, right around 2.87. All right, that seemed reasonable. All right, B, base added, but the moles of acid is greater than the moles of the base. All right, so I would expect to see the pH come up because my acid amount has decreased. All right, but it's not going to be crazy. All right, I do, however, also have some conjugate base present for that acid, which means it's not going to be just the acid influencing that pH. This is your buffer. All right, so we used our Henderson-Hasselbalch equation, and we found that the pH at this point was 4.57. All right, so we had a total volume at that point of 35, so 35, and we were at 4.87. So right around here. It's not going to be perfect, but all right. C, this is our equivalence point. All right, so the moles of the acid equal the moles of the base. So weak conjugate base present. All right, so because of that, I would expect to see the pH move up above 7. And in fact, we found it should be 8.72. All right, and we've added a total of 25. So 25 plus 20 is 50. Oh, whoops, I need to middle line here. I'll do that, just 8.72 at 50. Right around there. This is much harder without actual lines. Oh, sorry, I just need to move this a little bit because I did not give myself enough room here. 60. All right, and then D, this is going to be after the equivalence point. Oh, wait a minute, let me fix that. All right, at this point, the moles of acid are less than the moles of base. So strong base controls pH. All right, and we saw that at 60, we were all the way up at 12.23. So 12.23 here. All right, now you got to be careful. I mean, this looks like we should just draw a curve. But if we were taking data points all along, we'd probably see something that looks like this. All right, where our equivalence point is at a pH of 8.72, which is what we would expect. All right, we've neutralized the acid with the base. All that's left is that conjugate base for our weak acid. So we should expect to see a pH value above 7. All right, and then once we have excess strong base, that pH shoots right up. Okay, all right, so you can see that a weak acid with a strong base or a weak base with a strong acid, those titration calculations are going to be different because the conjugates are going to matter a little bit more when we deal with these weak acids or weak bases. All right. Also, when you have the conjugate pair present, then you've got a buffer and you have to calculate that slightly differently as well. Okay. So make sure that you practice these. All right. They're not complicated. Well, they are complicated. They are not difficult if you put in the practice and you really think about what's present in solution after the reaction has occurred. All right. So again, the visualization, the picturing in your mind of what ions are around, that's going to help you immensely.